Okay, so in this video, we're going to go through the things you need to make a functioning audio program, and then also go over the oscillator and the different things that it can do. So first thing I'm going to do is in my user files directory, I'm going to make two files. First file is going to be called os stuff, sure, .py, and then we're going to make another file called osstuff.mojo. And if you remember, the user files directory, or the directory where we're working, needs to have this init.mojo file, and it needs to be empty. Okay, so in the Python file, we need to declare some things. So we're going to say from Python .maudio import star. So that's going to import everything from the Mojo Python file. If we run that, it'll import everything in there. One of the things in there is list audio devices. So that will tell us all the audio devices that we have. And so I have this RME, that's my audio device, and that's what my system is using right now. So that's my default device. So if, but you can specify that if you want, and maybe we'll do that. So last thing that's always in these files is we're going to say audio equals, and we're going to declare the audio. So we need to tell it the block size. I'm going to use 128. Input channels 2, output channels 2. In device, why don't we specify that? And I can just copy this thing I've printed out. So if you are not using the system device, this is the way to do it. And out device, same thing. So great. And yeah, graph name is going to be os stuff, and the package name is going to be user files, because that is the directory that we are in. Okay, so that's how we would start the program. Now, we haven't made os stuff, so there's nothing to start. But that's your basic information, and we would say audio.start to get start audio, to get the audio running. So there's your basic Python program. Obviously, there'll be more complicated ones later, because we'll have things that use graphics and joysticks and such. So in this osstuff.mojo file, if we look at the file that we made last time, I'm actually going to put it over here just to help myself out. And also, I'll just say, like, this osstuff.py file, this Python file, is basically going to look the same in every program. So really, the best thing to do is copy and paste. I just wanted to go through it once and type it out. So in here, we have from audio import star. So that's taking all of the DSP that's in this directory and functions and stuff and importing all of it. That just makes it much easier to do things. So then we have a struct. Now I'm not going to look at this one. I'm going to look at this one, because this is our graph and we're going to base it on this. So we have a struct, and it has to be called osstuff. In our case, because that's the name of the Mojo file, right? So this is going to be the main struct, the main graph for the program. Great. So the next thing in here, now notice over here it says representable. We don't actually have to have that one, so I'm just going to skip that. You can have it. If you do have representable, then you have to have this function here to tell it to have the representable function, so that it can be represented by a string. But we don't actually need it, and we don't use it for anything in the repository. So we're going to use movable and copyable, and these are two things that absolutely have to be there. And all programs need to be, all structs need to be movable and copyable. Great. So we're going to make a variable called world. World is one of the most important aspects of this program. It's the main, it's like the main core of the program. All of the like global functions happen in there. It's also where the oscillators are stored. Oscillator wavetables are stored, the window wavetables are stored, and it deals with the messaging system going back and forth between Python and Mojo. So it has to be in every program, and it uses something called an unsafe pointer, which is a structure in Mojo for that points to items. So we have one world, it exists in our program, but what we're going to receive is a pointer to that world so that we're not copying and pasting it all over the place when the program's running. So it's just a pointer. And it is a pointer of type MWorld. So we'll talk about the difference between brackets and parentheses in a second, but they're very important. Inside brackets are parameters and types, and in this case, we're saying that we have an unsafe pointer of type MWorld, and we're just going to say var os, and that's going to be an os. Now we're just going to leave it plain vanilla for right now. So that is the structure definition and then the variable declaration right here. So any variables that we have need to be declared here, any variables in the struct. And notice that we tell it's strongly typed, so we have to tell the variables what kind of type they are. Okay, so next thing you absolutely need is an init function. All structs need an init function. And the init function has to say out self. That's the like minimum that the init function can have. And what that means is when it initializes, it's going to make itself. Itself is going to be created, right? And then we are going to receive a variable or argument, and that argument is going to be world, and it is of type unsafe, pointer to MWorld. Almost every struct in MMMAudio looks exactly like this. So if it's confusing, then know that it just needs to be that way. And so we're receiving the world from basically the main program that you don't see. And we're going to say self.world equals world. So we created that variable world, and then we're saying the world that we receive, we want to point to that world. So this is just going to be a pointer to the world. And so then self.os equals os. And os needs to be initialized. And so we're going to, where it says out self, we can ignore that, but we do need to tell it what the world is. Okay, so notice that I declared the variables up here. Now there are variables within os stuff, but since there are struct variables, struct members, when we're assigning them in the init function, we need to say self.world equals world. Up here it just says world. Self.os equals os. Okay, so last thing that we absolutely need is our next function. And since this is the main graph for the program, we need we're going to say mute self. So it's going to receive itself in the next function, and that's all it can have. So it can't receive any other arguments because it's the main struct. We'll very quickly start using structs that the main struct calls or instantiates, and in those cases they can have a next function that receives information. So, and then it's going to return. So this is the next function. It's going to receive itself, and it's going to return a stereo signal to the main program. So this could just return float 64, and that means it's going to return a float, right? So audio in MMMAudio is all floats. It's all float 64-bit floats. So, but instead we're going to say SIMD dtype dot float 64 2. And so what that's saying is we are going to return a SIMD vector with two variables. So it's a left and a right channel, right? So basically this is like two floats in a little vector that are going to be returned as a left and a right channel, right? So you can see that we have a little red squiggly here, and that's because we haven't returned anything. We've said that we're going to return something, but we haven't. So this is the next function. It's the function that's called every loop, every sample, right? So first thing we probably want to do is just get our oscillator working. So self.os.next, and the next function is the function we're calling. And within here, what does it need? The main thing it needs, so if you notice the arguments, the first argument is self. We just skip that one, right? Because it deals with that itself. The next thing we need is the frequency. And in fact, that's really the only one that is necessary, because if you look, well, it's not even necessary. If you look, all these other arguments have default values, right? So the default phase offset, which we'll use for phase modulation, is 0. Default trigger, so a trigger resets the oscillator back to the top of its cycle. And default os type, that one is one we're going to change in a second, but the default os type is 0, which is a sine wave oscillator. So we can just say right here, return self.os.next. I'm just going to make it a little quieter because it's going to be loud. So multiplied by 0.2. So this is like your most basic program. We thank MySaw for helping me out there. Your most basic program, right? So you imported the library, and then you make a struct that's movable and copyable and has just basically one oscillator in it. And that oscillator is going to make sound at 100 hertz. So it should be a 100 hertz tone. So if we go over to here, we have listed our devices. We can create the MMMAudio, and now it's compiling the program for us. And it's compiled, and we start it, and we get a sine wave oscillator. Okay, so great. So let's make this a little more more interesting. So I am going to, actually the first thing I'm going to do is I'm going to attach the mouse to this program. So something that's available in any program is the mouse. And so what we can do is we can say frequency equals self.world. Now, since world is a pointer, it has to have this funny 2 brackets at the end. Dot mouse x. So now the frequency would be basically a value between 0 and 1. So one thing that we could do is we could multiply that by maybe 200 and add 20, and then it'll go between 20 and 200. So if I now put freq in there, then the frequency variable went into next. So now if I move the mouse left and right, it should change the frequency between 20 and 220. So let's try that out. So that works. Great. So now you don't always want to have to do this kind of thing, this multiplication. So we have some scaling objects. So instead of that, I'm going to use something called linexp, which turns a linear value into an exponential value. So I'm going to say that it's going from 0. So the mouse is going from 0 to 1, right? And then we want that to go from 100 to, let's go to 12,000. So now that's going to make an exponential curve from 100 to 12,000. So let's give that a try. So if you notice something we hear there, so that's working, but something we hear there is the stepping, right? So you hear the value jump, because what's happening is the mouse is only getting a new value on every block size. So every 128 samples. So we want to smooth that out, and we're going to use a lag to do that. So we're going to make a lag struct. So we need to declare it, and then we need to initialize it. And I believe lag needs the world as well. And we can, in the init, tell it a different lag. This is like how long it takes to go from one value to the next. Let's just stick with the default. So so the frequency, now Mojo is a strictly typed language, but you can, if you hover over frequency, you can see that it knows that it's a float 64. So we could do a couple things. We could say variable, and we could also say variable float 64, and notice that it should accept that syntax because it is inferring the type. But we can be explicit about the type if we want. Okay, so now we can say freak equals self.lag.next freak. So now it's going to take the frequency, which is a float 64, put it into lag.next, and give us the frequency. So now that should smooth out the mouse. Right, smoothed it out quite a bit. And if what's not smooth enough for you, you can adjust that the smoothing time, the time it takes to smooth the signal. So you could change this right here. You could say 0.1 if you wanted to. So great. So now what I'm going to do is I'm going to show you that oscillator, actually similar to something like max or pure data, we basically have one oscillator. And the oscillator can be any of the different kinds of waves. So if we, in os.next, if instead of using the default os type, we change the os type, so notice that we can just enter the variables or the arguments from left to right in order, or we can do that. We can skip ahead and say the os type is now. Yeah, if you start typing os down here, you have os type as a struct, and os type. Right, we can choose the kind of oscillator we want. So I'm going to change it to, so there are sine wave, which is your standard wavetable lookup sine wave. Then there's non-band limited triangle, saw, square, band limited triangle, saw, and square. So I'm going to use, band limited saw. So then that's going to be a sawtooth wave that is basically made up of 512 sine waves, just not an infinite number of sine waves. So now if I run this, we should get a sawtooth wave. Now notice that there's all this nasty aliasing. So, if you're just using a sawtooth wave, like in the lower register, like below 1,000 hertz, you probably don't need to deal with, and you're not doing any frequency stuff like frequency modulation or phase modulation, it might be fine like in the low register. But we're going from 100 to 1200 hertz. So the OS struct actually has different ways of dealing with this. So if you hover over OS, you get a couple different, you notice the struct has something called parameters. So this is getting into the difference between parentheses in Mojo and brackets. So when declaring the OS variable, we can use parameters to change certain things. So number of channels. So I'm not going to get into that right now because it's a little bit complicated, but we're just going to stick with 1. If you do 2, the output of OS will be a SIMD with 2, with like a left and a right channel, basically. If that number has to be a power of 2. I'll just say that right now, but we're going to leave it at 1, 2 to the 0. And then the kind of interpolation. So we could say interp dot, and I can hover over interp, and it tells us the different kinds of interpolation that are available. So no interpolation, that's going to sound terrible. Linear interpolation is like standard wavetable lookup interpolation, quadratic, cubic, Lagrange, four variable Lagrange, and then Sinc interpolation. So let's just leave it at linear right now. And then the last parameter for OS is oversampling. So we can give it an oversampling index. So basically, if the default is 0, so there's no oversampling. If you give it a 1, then it'll be 2 times oversampling. A 2 will be 4 times oversampling. 3 will be 8, and a 4 will be 16 times oversampling. So if you give it more oversampling, it will take up more CPU because it will process. So if we have 2 times oversampling, it's going to do twice as much processing. It's also going to add a filter in there. So this is something to be, considered. But let's just do 2 times over a 2, so 4 times oversampling. So notice now this has a little squiggly under it. It's not happy. So this needs to reflect this. So we could actually just copy it, but we're going to say, I'm going to just put it in here, 1 interp dot linear and 2. Okay, so that now we have an oscillator that is a sawtooth wave, and it's going through 4 times oversampling internally. So let's hear what that sounds like. So you can hear that there's still some aliasing, but it's not, it's much better, right? So basically what's happening is doing 4 times oversampling, I'm at 48K. So it's going, basically the oscillator is running at 192. And so, but a sawtooth wave has lots of partials. So up in that upper register. So with sawtooth waves, square waves, we probably don't want to do linear interpolation. We actually want to use Sinc interpolation. And Sinc interpolation is a special kind of interpolation where it basically takes 8 values from the oscillator buffer, and then as you go up per octave, each octave that the frequency goes up, the oscillator looks into the buffer in such a way that it removes the top octave of harmonics. So that's a whole other video, but we're going to use Sinc interpolation with 2 times oversampling. And basically Sinc interpolation is always removing the top octave. So as you go up an octave, the top octave is removed. So there shouldn't actually be any aliasing above 1 octave above the Nyquist frequency. So that's why I'm only doing 2 times oversampling. So this should actually sound pretty good. So let's check this out. So that's pretty amazing, right? So the there's almost no aliasing, or there is no aliasing. And in that upper register, it just sounds like a sine wave, because using Sinc Interpolation, it basically is. So in this video, we built our first struct from scratch, and that struct is being directly used by MMMAudio as the primary graph for audio. So in the next video, we're going to show a struct of structs and how we can build up a program by building up structs that contain other structs.